Oh, it's that times how much it costs to lose now. So, once you have that fraction there, it's gonna be that times that difference. That's gonna be the loss.
Have a good one.
You do.
Have a good break, guys.
Alright. Yes. So at some point, you should have the fraction 15/55. You don't have to reduce it to 3/11, but the math is fun. Okay. Inverted to 0.9.
Oh. Yeah, should be.
Yeah. Yep.
Sorry, I don't,
So 80 minus 65 is 15.
no, see, I didn't, the area, the large area, that's where I was going. But I shouldn't have been doing that.
It's, for the first time period, it's how much it actually lost divided by what's the most it can use. So,
Okay, that's what, okay. Okay.
let's see where you're stuck. You want to just move on. And I think I'm seeing people with answers with units too, so. Yay. Alright. One more minute, then we'll talk about it as a group.
so let's take a look at this as a group. Also, I saw my note, and so I remembered, just flash back to the beginning, you take the degrees Fahrenheit and you add 458.67, you get the temperature in Rankin. All right, so in the first 2 hours, it loses 3/11 or 15/55 of what it could lose. Because the maximum it could lose is that difference right there, which is 55 degrees Celsius. The actual amount of loss was this amount, which is 15 degrees Celsius. So we now have set the fraction for the rest of the problem. So in the same time frame, so in the next 2 hours, it's gonna lose the same amount, same fraction, same percentage. But now the most it can lose is that difference. So that's 40 degrees Celsius, the most it can lose now. So the actual temperature change is going to be whichever fraction you like, 15/55 times 40 degrees Celsius. And so multiply that out and 10.91. Unless I wrote it down wrong. That is the amount that is actually gonna lose. And so the final temperature at this point would be 65 degrees Celsius minus 10.91 degrees Celsius. And we get 54.09 degrees Celsius.
So that's why I stopped at 40, and I just did not know what to do with 40.
Yeah, I don't have a different way of saying it right now.
Okay.
If you go to the Blackboard site under coursework, the chapters 15 through 18, thermodynamics, etc. And there's a video where I go through, I think, 2 examples. Perhaps I had better wording then, look at it differently then.
So we're doing 15 times 1555 times 40.
15 divided by 55 times 40. But you're not getting 10.91?
Yeah, now I am.
Okay.
That's because I'm doing 15 divided by 55 times 40, I didn't do that before.
Ah. Do you prefer by setting up like 2 fractions equal to each other?
No, I just didn't know that's what I needed to do.
Okay. All right. So we've talked about the implications of temperature exchange. We've done it where ultimately energy is conserved. If you look at a big enough environment, here's a situation where it looks like something is losing energy and nothing's gaining energy, but it's just that the environment, the room, whatever it is gaining energy, but it's spread out over so much we don't notice it. Still working in the assumption energy is gained. If we think back to when I did Q equals MC delta T, that was the change in temperature based upon how much energy I put into it. But that assumed that the object stayed whatever state of matter it was before. It maintained its phase. So it was solid to begin with, stayed solid, liquid stayed liquid, gas stayed a gas. Now let's deal with what happens if it has to change type, or change phases, or change states of matter. So I introduce to you latent heat of fusion and latent heat of vaporization. Very much similar to the specific heat in the meaning of the heat there. There's two different symbols I will see for the latent heat of fusion. I think I have used them both at various points, and so latent heat of fusion, sometimes I use an L with a subscript F, and sometimes I'll use a C with a subscript F. Heat of vaporization, sometimes L with a subscript V, and sometimes C with a subscript V. The units, I guess SI units, the SI of, I'm going to stick with the C notation here, would be joules per Kelvin. Try that one again, joules per kilogram. Because when you're doing the phase change, there's actually not a change in temperature. When ice melts, first you get ice up to the melting temperature, it melts, and then it increases in temperature. While it is melting, it is not changing temperature. What's happening is we're increasing the potential energy, we're getting the particles to move farther apart from each other. Now in reality, some of the ice that melts will start to heat up before all the ice is melted. We will not make that assumption. It's all gonna happen, sequentially. However, it doesn't change the essence of what I'm saying here. So let's talk about the three major phases or states of matter. We have the solid, we have the liquid, and we have gas.
Excuse me, mister.
Pardon?
Excuse me.
Hmm?
The C is the specific heat.
Yes, I just, sometimes I've used capital N, sometimes I use a C. I'm gonna use C for this course,
Okay.
right now.
Okay.
I'll probably just do a quick check to see what Hewitt uses, I don't remember.
For the specific heat?
Yeah. Or does he use anything at all? Looks like he doesn't use any symbol at all, so I'm free to use whatever I want.
Oh.
All right, so if something that goes from solid to liquid, what do we call that? I was looking for more specific vocabulary. Think about, pardon?
Phase change?
That's what I'm going for. It's melting.
Oh. So you step one from a solid to a liquid?
Yeah, it melts.
Is it?
That's what going from a solid to liquid is, it's melting. If something goes from a liquid to a solid,
Is that evaporating?
not liquid to solid,
Solidify.
Oh, wait, no.
or,
Freezing?
yeah.
I was thinking something else.
Yeah, yours is coming up. All right, so now freezing means you're taking molecules and you're sort of binding them to each other. In other words, you're fusing them. So the latent heat of fusion deals with this transition. So the latent heat of fusion deals with this transition. Freezing or melting, either way. Solid to liquid or liquid to solid. In one case, you're putting energy in, the other case, you're taking energy out. All right, liquid to gas. 100,000 chance. Liquid to gas
Evaporation?
or vaporization. If the process takes place because of you pumping, because of heat, because of temperature, the temperature's high enough, that's also known as boiling.
Wait, so why are we putting vaporization to evaporation?
I guess evaporation works.
Oh, I didn't know if there was a specific reason.
I was not distinguishing, so evaporation. Evaporation can happen at any temperature, boiling happens at a specific temperature, or a general temperature. If you're going from gas to liquid, guess I'm changing my parts of speech as I go, but that's just the way I do it.
Condensation.
Yep. And that's what most of us experience on a somewhat regular basis. Solid to gas.
I don't know anything that goes from gas to a solid.
Well, this is solid to gas. Actually, you probably have seen it, but not realized it. It's called, first off, it's called sublimation.
Sublimation?
Sublimation. There's an I there. Now, the times that I have seen the experience of it is, well, I have seen dry ice before. Dry ice does it, because you get a block of dry ice, it will turn to vapor. It doesn't, you don't see a pool of carbon dioxide. Also, snow will do it. Some snow melts, but not all the snow melts. Some of the snow will actually go into vaporization, will go into gas form and skip the liquid phase, or the liquid phase is so fast that we don't notice it. There was a video on the internet where somebody took a blowtorch to snow and showed that, you know, there wasn't much water that came out of it, and was making the claim that therefore the snow was some other chemical, it wasn't really snow. And then with, you know, the respect that you generally see on the internet, someone said it's called sublimation. It's not some mystery here. So those are the ones that I had done. I had to look up the next one at some point in the past 10 years. Because gas to solid was not something that I had dealt with. So that's called deposition.
Is that a,
What's
what
that?
does
I heard a
that?
word, that I never knew that was.
It's usually associated with lawyers,
I was
Yeah.
gonna say, I agree.
but it's a different meaning here. Basically, you think about something depositing.
Isn't sublimation a way they like print t-shirts? Sublimation, isn't that a way they print your t-shirts? I feel like
Oh, I have not heard that.
I don't know, I feel like I've read that somewhere before.
That's possible. Except sublimation would be going into gas, I would think.
Yeah, I don't know how it,
If you happen to run across something that talks about that, then by all means, I'd really like to see that. Oh, and then vaporization, heat of vaporization is associated with this process. Now, this process, obviously, I don't have a separate latent heat. But the latent heat for deposition or sublimation is just the sum of the other two.
what turns from a gas into a solid?
I would imagine that, I don't know for sure, this is speculation, but if I took, a gaseous, I assume that there are some gases that if you put them in the right pressure and temperature, that they would suddenly sort of form crystals. But I don't know. I have not seen it. That's why I had to look that one up sometime in the past 10 years.
Maybe it could have been a snowflake.
It's possible.
From the sublimation. I don't know, leave me alone. Yeah, but-
All right, I'll stop harassing you
okay.
for now.
So.
Isn't it just water that freezes really high, isn't that what it snows?
Right, yeah, that's all I was like, nah.
In which case it would be the whole freezing bit. All right, so let's just go through, an example here. So first off, the formula. When you're dealing with phase change, that's equal to CF or CV times mass, generally mass comes first. MCF or MCV. Depending on which part of the process we're doing. To give you some ideas of numbers here. So for water, the specific, the latent heat of fusion is 330,000 joules per kilogram in SI units, or in more convenient units, 79.7 calories per gram.